So, hello everybody. Welcome to our Dresdner Planerforum. Today I have the honor to welcome Birgit Kopainsky, who will talk about how can system dynamics contribute to transformation in social-ecological systems. She will get some support from Daniel Klein. So we have two persons today who will give us insight into system dynamic modeling and two cases of application, two cases taken from construction and building sector. In one case, the second case from agriculture sector. And one case is taken from the context of a developed country, and the other case of a developing country context. So, but first I want to introduce the both speakers. Birgit is introduced in the letter of introduction that is provided on the internet page of our institute. She is professor of system dynamics at University of Bergen, Norway, and holds her PhD in agriculture economics from ETH Zurich, and a master degree in addition to that in geography and environmental studies from the University of Zurich. So she's a very well-known expert in the field of system dynamics, and to just take one aspect, she's the first ever female president of the System Dynamics Society. So there are a lot of other things I could tell, but I would not spend too much time on that. Sorry. And Daniel Klein, he studied economics, and in addition to that, he worked on the topic of sustainability management. And in this context, he used the system dynamics approach in his research. And in addition to that, in this research, he follows a PhD project. And his supervisor is Birgit Kopainsky. So they know each other very well. And we are very happy to have you today in this IOER forum. And I would say the floor is yours. Maybe one remark, one additional remark. So we make a record of this session. So you see it on the edge of the screen there, that we record this session to be able to go through the session afterwards again. So it's important that everybody is aware of that. And I discussed it with Birgit and Daniel before. So if you have any questions, if you do not understand something they tell us, please do not hesitate to ask. Also to ask, to interrupt them and ask them for clarification, or give us a note in the chat, so we can decide whether we should shift these questions to the end, to the discussion, or if we give her a note that there is an important question. They have planned to present about 45 minutes. And so we have, again, more other 40 minutes for discussion. So thank you very much. And the floor is yours, Birgit and Daniel.
Thank you very much, Georg, and thank you everybody for the invitation. It's a pleasure to speak to you today, and I want to particularly acknowledge Daniel, who helped me out in my desperation to talk about system dynamics in the construction industry. I can talk forever about system dynamics. I get onto very shaky ground when I have to talk about system dynamics in the construction industry. So that's your show, Daniel. I'll support you when it comes to reinforcing and balancing feedback mechanisms. Let me try to share my screen here. Daniel, do you see my screen? I see you. Okay, great, wonderful. So we planned a talk today that combines the methodology of system dynamics and focuses on methodological aspects such as, how do you build models, what can you do with these models, what can you get out of these models, and what can you not get out of these models. And we're not doing this kind of lecture style the way we do it at the University of Bergen, where we teach a full master's program in system dynamics, and we cover all kinds of application domains, ranging from the restaurant industry through public health care to applications in ecology and economics. But much rather, we look specifically at the case of transformation in social ecological systems. And Georg has already mentioned that. We picked two case studies that, although they're located within the social-ecological systems framework, they are fairly different. So they look at agricultural stuff, they look at the construction industry, at the developing country context, at the developed country context. And thus we hope to explore a little the application space of this methodological approach. Now, much as I love system dynamics, maybe you don't know all that much about it. So we start our presentation with a module on that answers the question, what the hell actually is system dynamics? And then we'll spend the majority of the time on point 2, on key question 2, which is what insights has system dynamics generated so far for social ecological systems research. So we will spend the majority of our time on the actual application on the 2 case studies, and then take these 2 case studies to talk about question 3, how can system dynamics contribute to transformation in social ecological systems? So let me start with giving you a quick overview of what system dynamics is. First and foremost, you can debate, but first and foremost, to me, system dynamics is a method. It's not a paradigm, it's not a philosophy, it's not a religion, it's a method for developing models. And when we talk about models, we talk about a combination of 2 things. We talk about qualitative models that manifest themselves in the form of diagrams. And then we move on to developing quantitative computer simulation models. But I'll talk a little about these qualitative diagrams in my case study to illustrate already the kinds of discussions that you can facilitate with this more qualitative step in the modeling process. So system dynamics is a method for developing models, and not just because we love model building, but because we want to learn about the dynamic complexity of a problem. I'll get back to that. And we want to understand the sources of policy resistance. So we want to understand why building more roads leads to more traffic. That's a classical example of policy resistance. So that with this deep understanding, we are better equipped to design more effective policies. Now, what does dynamic complexity mean? Dynamic complexity means that with system dynamics, we look at problems that unfold over time. That may sound very intuitive, but it takes a little bit of mind shift or of a change in perspective to always look at an outcome, at an output from a simulation model that has on the x-axis time. So we don't look at supply and demand curves, we look at development over time. And complexity, we'll get back to that. Complexity is everything that has to do with feedback loops, accumulations, and nonlinearities. And I've already mentioned this. We look at policy resistance. We try to identify sources of policy resistance, because policy resistance is where well-intended policies have unintended consequences. It's where things go wrong. And we try to be prepared for that in light of this latter step of designing more effective policies. And finally, by doing all that, by looking at dynamics, at feedback loops, at policy resistance, we want to learn. We want to learn about the system, and we want to learn about how to design more effective policies, but also how to transfer insights from agriculture to the construction industry and back. System dynamics is a wonderfully weird method that is grounded on the one hand in nerdy things such as mathematics, physics, and engineering. It has to do with nonlinear dynamics and feedback control systems. But then it very much draws on social science, on economics, and on cognitive and social psychology to incorporate decision-making, to very explicitly look and re-represent the people who are inside of these systems and who make decisions about these feedback control systems. The method dates back to the 1950s, where it was developed at the Massachusetts Institute of Technology and originally applied more to the industrial sector to help managers improve understanding of industrial processes. But very soon it started being applied in what today we might even call social-ecological systems. At that time, they were more called urban dynamics or the limits to growth. But so we have a long history of applications of the method in social-ecological systems. So in systems where the environment interacts with societal questions, with economic questions, with people, with humans who interfere in the environment. And when we conduct system dynamic studies, what we try to do is we try to step away and not focus very much at events. So we don't look at a drought hitting a country, but we try to step backwards, adopt a dynamic perspective, and look at problems as manifestations of patterns over time. So it's more a series of droughts that starts being interesting from a dynamic perspective. So we look at patterns of behaviors, at trends, and how they unfold over time. And by applying these qualitative model diagrams and the quantitative computer simulation models, we aim at understanding the structure, so the processes that drive problematic behaviors, the processes that are responsible for the behavior over time and for these individual events to occur that catch our attention. And I've mentioned this before, learning is a big thing. So by moving away from events and looking at patterns of behavior, at system structure, we try to learn more about the system. We try to refine our own mental model so that we're better equipped to develop policies that do not have unintended consequences, that do not backfire. I think, yes, so I'm going to skip this because we're already running out of time and we don't want that. So we have this modeling process that starts from understanding the system, defining the problem, moving through the qualitative step of model conceptualization, through the quantitative model formulation stage, where we eventually simulate and use simulation for policy analysis. What we want to focus on today is not just this nerdy modeling process where we identify cause and effect relationships, variables and their interrelations, and then come up with equations that quantify these relationships. We want to focus today on something that I consider fairly unique and maybe informally put very cool about system dynamics, which is that there is a strong body of literature that uses the system dynamics modeling process in a participatory way and engages stakeholders at each step in the modeling process. We can call this group model building or participatory system dynamics or community-based system dynamics. If you really want to dig into the finer details of what the difference is between these approaches, we can go there. But for our purposes today, it's just important that, especially when we talk about transformation and sustainability and changes in decision rules and in behavior, participation and engagement of stakeholders along the entire modeling process seems pretty important. Otherwise, we end up with a model and with what modelers usually complain about, that first of all, data is never there and policymakers never listen. And no wonder, if you develop your model behind your desk and you come up with the optimal solution, it might not come as that much of a surprise that people don't probably trust your model as much as you do. So the two case studies that we want to present to you today are both examples of a participatory modeling approach where we worked with stakeholders from the get-go through to the very end of the project. So let's move on to the second block, to the kinds of insights that system dynamics has generated so far in social-ecological systems research. And I'll start with my own case study, which is, it's a little exaggerated saying it's my own case study. It's a case study that I did with a previous PhD student, not with a current PhD student, but with a previous PhD student. I do feel much more competent to talk about this because it's right down my avenue. It's agriculture. It has everything to do with farming, with droughts, with water and nutrients. So it's about, this case study is about maize production and maize consumption in Guatemala. And you might wonder, why on earth would that be interesting? So to start with, when we look at the country of Guatemala, this is a country that depends quite heavily on agriculture. And much more importantly, it has severe problems when it comes to food security. So it faces severe challenges when it comes to food security or the challenge of providing enough nutritious food to its population. But then this challenge is exacerbated by the fact that climate change is hitting the country really hard. So Guatemala, for what it's worth, is among the top 10 countries, certainly when it comes to being exposed to climate change. So in this case study, we look at the resilience of agriculture systems, and more specifically, the resilience of food affordability to climate change, and very specifically to droughts. So we want to understand here how people experience food insecurity, and especially how droughts increase their vulnerability in terms of food insecurity, and then of course what can be done to alleviate this challenge, to become more resilient or more robust against this pressure. So if we look at the food affordability, I said before that in system dynamics, we're interested with dynamic problems, with development unfolding over time. So what we see here unfolding over time is the amount of food on average that is consumed per person per day. That's the amount of food that I would love to consume per day to lose some weight. But if this is your normal diet, and you compare it to the 2,000 roughly calories that you need to lead a healthy life, that doesn't look too good. So here's our challenge. And the way we went about studying what underlies this problem, how this problem is exacerbated by droughts, and what can be done to mitigate the impact of droughts. As I mentioned before, we engaged in a group model building process with quite a variety of stakeholders. And so what you see here is a rough sequence of activities that we conducted with farmers, NGOs, government representatives, and what did I say? And university researchers. So we try to cover most of the major players that have an influence on food security, and started with conducting interviews and then engaged in iterations where we conducted a first group model building workshop, went home, did some modeling, went back to the group, did more interactions with and discussions with the group, identified policies, went home, came back with results, and revised these results and insights. So let me split the presentation of the results that came out of this process into two categories. The first one is the first part of the analysis focuses more on the qualitative modeling aspect that I mentioned. At the outset, I said that system dynamics is a method that uses diagrams and computer simulation models to study problems unfolding over time. And so when we talk about diagrams, what you have here, to us, they look super intuitive. To you, they probably look more like spaghetti diagrams. But what we have here is a representation of individual, or let's say stakeholder-specific perspectives on how the problem of food affordability arises. So up here in this upper left corner, we see a kind of a translation of what central government delegates say about why food insecurity arises. Here we see a translation of interviews conducted with NGO representatives. This here is a translation of interviews conducted with researchers. And this one here is a representation of the mental models of farmers. And what's striking is that at the end of the day, everybody talks about food affordability. I mean, we ask them about food affordability. So obviously they all talk about food affordability. But the government basically says, well, food affordability and thus food consumption is simply a matter of how much money farmers have. And NGOs and university researchers seem to agree. Whereas farmers say, sorry guys, but this is a little more complex. Obviously, it's important that we have money. Obviously, our household cash is important. And the price of the food determines how much we can buy. But for us, the key point is that there actually is food. So the farmers are the only stakeholder group that don't just talk about monetary variables or monetary concepts, but that talk about practical issues such as having food stored locally, somewhere locally where they can access it and consume it. The other thing that's probably striking is the government has a fairly straightforward view of how this problem arises and how this problem can be solved. Basically, it's let's spend money on subsidizing fertilizers, because the more fertilizers farmers use, the more yield they generate, then they can sell more food, and that increases their wealth, and we're done. Farmers look at this a little more in a little more differentiated way, and university researchers, of course, they go crazy. They go like, oh yeah, well, yield is not just a question of fertilizers. Yield is a question of soil organic matter. It's the amount and quality of land. There is something about water in the soil. So you see, all these different stakeholders have fairly different individual perspectives of how the problem arises, and implicitly what can be done to alleviate the problem. And so what we did based on this initial information was to just map these different perspectives in a first group model building workshop and say, so these are your different ideas or insights about the situation. And we spent an entire workshop kind of patching it all together. you probably won't remember the previous diagram, but there were no contradictions in the diagram. Nobody said that more nutrients lead to less yield. It was more that people focused on different elements in the system. So it wasn't a very contentious exercise to put everything together and try to build a big picture. It was much more a question of negotiating a shared understanding of how all these things relate to each other, and how they affect our food affordability or food consumption. And I'll talk about some of these elements in a minute. But basically what we can see here in this integrated perspective is we have some processes that talk about economic things, so about storing crops, maize reserves, the price of maize on the market, how much money farmers need to spend on food, and how much cash they have available. Then there is a sector that talks about decisions on household level. On household level, basically farmers generate revenue that they invest either on fertilizers, irrigation, livestock, or in food. And then there is the natural system. So here we have our social-ecological system, the social and the ecological system that interact in some fairly powerful reinforcing feedback loops. The other thing that came out of putting everything together was, yes, now the individual pieces of the puzzle started forming a bigger picture, but in the course of these productions, in the course of these discussions, we also identified a series of feedback mechanisms that nobody had talked about before. And while we have a powerful reinforcing feedback loop here that basically the government believes so much in, which basically says the more maize I produce, the more maize I can sell, then I have more revenue. That means I have more total available cash, which I can invest in fertilizers. This increases my soil organic nitrogen, improves my yield, and I produce more. And all we have to do is make sure that this feedback loop works in a virtuous way. That means that it goes from more to more to more to more. What wasn't very clear to anybody involved, but also only came out in the course of these discussions, was that as soon as farmers start observing higher yields, they expand the area that they plant. So they expect higher yields, they expect higher revenues. They start planting more maize, or they start cultivating more land with maize, and thus they increase the water requirements. And so suddenly the finite resource of water needs to be spread across a bigger land area, and which reduces eventually the yield. So that was interesting. There were some other smaller policy resistance mechanisms that came out of this discussion that was only possible by combining all these different stakeholders. And the other thing that came out was that it was actually only the university people who talked about livestock. And so by having also this perspective contribute to the discussion, there was an increased awareness that a potential entry point for policy was to invest in livestock, which has a number of effects. But I need to move on. So that's all the kind of cool things, insights that were generated without a computer simulation model, just with making individual stakeholder groups' understanding of the system visible and negotiable, so that everybody could start talking about the same thing and seeing their perspective in the bigger picture. There we go. So analysis part 2 is where the computer simulation model comes in. And Daniel will show you an actual computer simulation model. So this is just a teaser. We use this diagram, did some equation formulations, and ended up calibrating the simulation model for 2 case studies. One that has an absolutely unspeakable name, and another one that is maybe a little easier to pronounce, but maybe we could just call them A and B. That might make things easier for the discussions. So what we see here is historical behavior of food consumption over the last 20 years. And we also see that in the absence of big shocks, there isn't very, very interesting dynamics going on. We do see here that there start being some droughts. So food consumption is coming down a little, but basically just this reproduction of the historical behavior helps us build some confidence in the utility or in the usefulness of the model as a tool to explore different drought and policy scenarios. So then we went on by saying climate change is most likely here to stay. So what does this do? What does climate change do to the future of food security or to the future of food affordability? How will the system react to further disturbances in terms of droughts? Will it remain stable? Will it, will it bend but eventually recover, or will it break? So will a disturbance be visible, and how much of a disturbance can the system tolerate before we see some changes from the baseline behavior? I'll skip that. And so we calculated, we ran a series of Monte Carlo analysis to find out where the threshold value is between baseline behavior, no deviation from the baseline behavior. That's what we call the hardness. And then how much more of a disturbance can the system tolerate when it bends before it completely breaks and never recovers, which is what we term elasticity. So when we run these kinds of analyses for our case study A and B, we see these three regimes, basically. We see the stability regime, we see the adaptation window, and then we see the transformation window where the system breaks and transforms into a new system. And so these weird percentage values here, hardness 28%, elasticity 34%, what they indicate is that in case study A, the system tolerates a 28% decrease in annual rainfall per year before we see a change in the outcome function. So up to 28% decrease in annual rainfall can be tolerated and compensated by the system before we see a change in the amount of food that can be consumed. In case study B, it's a little less, it's 23%. But what's interesting here to see is not so much 23 versus 28%, but that this window, I call this the window of opportunity, this adaptation window, where we do see a change in the outcome function, but eventually we see a recovery. This is very small in this case study up here, in the case study A, and it's much larger. It's up to 58% reduction in rainfall that it takes before the system collapses as we know it today. And we can discuss about the structural origins of this. Basically, it's because this case study B down here has a little more diversified household structure, where households not just produce crops, but they also have some form of livestock. They have some form of poultry that gives them a little more maneuvering space when it comes to additional sources of income and additional sources of food. So then we went back and said, okay, that's the outlet, that's the baseline situation, that's how much we can tolerate before we bend or break. What can we do to change, to improve this? And there are different entry points in this system that range from subsidies, either subsidies for fertilizers or subsidies for irrigation, to strengthening of this of the livestock loop, and introduction of emergency food banks. And when we go back to the diagram, we see that this window of opportunity changes somewhat with the introduction of these policies. So now we need to compare up here the baseline situation for case study A, the baseline situation for case study B, and we see how the different policies shift the stability and the elasticity frontiers either to the left or to the right. And we see particularly that the government's favorite policies, increasing subsidies to fertilizers or maybe also to irrigation systems, don't seem to do a whole lot. Not when it comes to stability, a little bit for adaptation, but they're not very effective. What's much more effective is the introduction of or the promotion of livestock and poultry farming. And again, this has to do with these different stocks in the system, the stock of livestock that helps buffer revenue losses, and the stock of household food, the stock of food reserves that increases the adaptability window here. With that, I want to leave it for the moment for the first case study and turn it from maize and poultry in Guatemala to Daniel and the construction industry in Switzerland.
Thank you very much, Birgit. Fantastic introduction. There's a lot I can already take away.
Yeah, you should. I took up way too much time.
Exactly. So what I'll be talking about is the Cubic project, where we looked on the construction material industry in Switzerland and their transition towards a more circular / sustainable economy. And pretty much 3 years ago, we started the process. Same as Birgit, we got together a group of people that represent relevant stakeholders in our system of interest. And they ranged from industry representatives, for example, construction companies who mine gravel, recycling companies, environmental agencies, NGOs. So pretty much everyone who has a say in the system or is impacted by the system. And I think that's already clear from Birgit's talk, but I like to stress that it's very relevant to get all these perspectives in. And in the first workshop, we formulated a common problem, and that was that the access to gravel quarries that consequently lead at the end of their lifetime to disposal volumes for excavated material and also construction demolition waste is becoming scarce. And that's a problem, especially in urban areas. So what we see is that transport between regions are increasing. So material is transported further and further, while the potential for recovery is not fully exploited. So when I talk about recovery, I talk about two things. And that is the excavation material. So plainly said, imagine you construct a house. You have an input of gravel in the form of concrete, and usually, especially in urban areas, it's a trend to dig deeper for parking garage. So you excavate material that contains natural gravel, and also you deconstruct old houses. Hence, you have construction and demolition waste, which could be recycled. And it's debatable, but technically you could recycle up to 100% of such waste. And we were interested in what is the role of public policies and business strategies. We know there's some form of interaction, so public policies influence business strategies, but also are in return influenced by such strategies. Because depending on how the business strategy in one region develops, that can change, for example, material flows to which public policies then react. And we were interested in which barriers barriers and drivers are available on that transition. So if we move to the next slide, we see a very simple part of the model, which I would like to use to show you how the models look like if they are quantified. So we have several stocks in the system, and we have flows in between those stocks. So here we mapped out the process of, we take gravel reserves into our cantonal structure plan. These are approved by the local communities and thereby end up in the stock of approved gravel quarries. Then companies extract the gravel, thereby reducing that stock. And the gravel extraction, especially in a country such as Switzerland, which is very small, we want to make good use of space. So gravel quarries in our model always result in disposal volume, which you can then fill with waste. And that waste is not recycled waste. So everything that you do not recycle ends up in a landfill. And you see on the bottom, there are a couple of arrows going into the landfilling, and that is the construction and demolition waste, which is not recycled, so to speak, the leftovers. And on the top, we see the recovery of gravel from excavation material. So essentially, there's a feedback loop going. So if our disposal volume is getting scarce, it's attractive for companies in a region to increase the recovery of materials because there is no volume for disposal. And if you recover more material, you don't need to extract that much gravel because it's also not attractive for a company to sit on a pile of gravel. And on the bottom, we see a similar feedback loop where we say that, well, if our coverage of gravel quarries is reduced, the same happens to the construction and demolition waste. And what's interesting is that, especially on the upper feedback loop, it's also a policy mechanism. Those are not only actions taken by companies, but if a region is facing a shortage of disposal volume, they may decide to grant additional volumes in the form of landscape adjustments. So, for example, a gravel quarry that is no disposal volume can be filled up to, let's say, 150%. So in a nutshell, you can kind of increase here. It's like you fill up the landscape. And I would like to use that structure and give you a peek at my model. I'm going to share my screen, and you should be able to see my slide now. And what we do is we use two regions, region A, region B. Region A is an urban city, and we're going to look at the material flows and then see how will these develop in the future. And we use different scenarios to do so. So if I run my model, so far nothing happens, right? We see here on top the aggregate demand for the region. We see here the excavation material that is leaving the building stock and has to dispose in the region, and we see the construction demolition waste. And now I have different policy mechanisms. So we have different scenarios. I will take example one, which is the greenfield development, where you build on the countryside. So you don't build that much within cities, but you use empty land. So that means you will need a lot more primary gravel or gravel in any form, but it doesn't really change the amount of local excavation material. It doesn't really change the construction demolition waste. And what I can see now is what happens. And I will focus on the most relevant things, which is comparing two different regions. In region A, we say, well, it's an urban center. Building on the case of Zurich, they already recycle almost everything of the construction demolition waste, but not the excavation material. In region B, in general, on the rural side, you don't recycle that much, but in that case, there's a clear tendency towards more recycling. And within that system, it is a policy goal to be self-sufficient for both your material demand, but also for the waste. So in the long term, region A is relatively self-sufficient, region B more or less so. What I can do now is I can change the structure of the system to see how that impacts the behavior. What we see here is essentially the same graph I showed before, right? So we have the new gravel quarries being introduced in the regional planning system. They are granted, they are extracted, etc. So when Birgit said we are playing with models, we are using these models to understand how the system changes, we can say, okay, what happens if in region A, I completely restrict the availability of gravel? So I want you to focus on the graphs where you see the stocks, so the potential in the region, which is the blue line, and the red line is the licensing. On the right side, we see the flows, so the introduction of new, the licensing, and the extraction itself. And this is a nice example on delays within a system, right? So if we don't take further gravel quarries into our structural plan, naturally, after a couple of years, we won't be able to license anymore. For the industry, that means, well, in the short term, we can satisfy the local demand. But after a while, there isn't enough gravel and extraction dies off, so to speak. So we haven't changed the material flows. This is purely from an endogenous perspective of the system. And now we see, well, once the extraction dies off, every material needs to be recycled. But like in the case of Birgit, there is a certain bend or break idea, right? What we see here is that region B, in the short term, they start to recycle more material, but it's not a trend that came to stay. So in the long run, recycling is decreasing again. And so we slowly iterate our knowledge of the system and learn why are these trends happening? What are the drivers of such developments? And then we build on that, do more and more policy analysis, and most importantly, learn together with the people in our system. So just by having such a simulation in front of them, people naturally consider more broadly, what do we need to think about if we talk about long-term planning for our region? I'll leave it at that, and Birgit can start sharing again, and I'll provide some of the learnings we so far generated.
Great. I need to refind the screen. There we go. Okay.
So the insight so far is that the construction material is an inert system, so it's very reluctant to change, and if it does, it's very slowly. That is due to a lot of aspects, but the first ones that come to mind is that if you increase recycling, that requires adaptation of standards, norms, etc. So that doesn't happen overnight, it takes time. Using scenarios in that model, it kind of shapes the scope of action. By that I mean it opens people's brain up to the possibility of what will happen if we satisfy our growing population that way or another way. So population development, spatial planning, it kind of goes into hand in hand with resource management. And from a regional planning perspective, we saw that region A's development is always interdependent with the development in region A. I guess Georg can also talk about that quite a lot, but kind of the construction of urban structures is very closely tied to resource usage in the hinterlands. And one interesting insight or thought is that circularity or circular economy is easier to achieve in a society with growing resource usage, because the competition with existing primary products, let's say, isn't that hard. And with that, I'll pass the speaking stick to Birgit.
Excellent. Thank you, Daniel. Now we need to wrap this up in -4 minutes. So let me move on to the third question of how system dynamics can contribute to transformation in social ecological systems. And we hope that these two different case studies of systems have shown a little bit that there are a couple of properties that make social ecological systems counterintuitive. And among them, we have dynamic complexity. Things change over time. These systems are characterized by feedback loops. There's some emergent behavior. We haven't talked much about that. We have nonlinearities in the system. We have leverage points that tip the system from one regime to another. There's path dependency. That's a repetition. Domains of stability and tipping points, just to iterate the point. And in addition to all of this, kind of objective stuff about social ecological systems, what makes them hard to tackle is that we have multiple stakeholders with multiple perspectives and priorities. And the other thing that's a little challenging in these complex systems is that there are no such thing as easy silver bullet solutions that are easy to communicate. I mean, just the example that Daniel, or the conclusion that Daniel shared at the end, that circularity works better in growing markets, to me, that's difficult to communicate. That's an example of something being difficult to communicate. So how can system dynamics contribute to all of these changes, or all of these features? I would claim that the modeling language and the way of analyzing models can help deal with a number of these features that social ecological systems have. It can help us deal with change over time, with nonlinearity and domains of stability and tipping points. And the diagramming conventions and some of the output features that the approach has, and particularly the process of involving stakeholders throughout a modeling project or throughout a series of modeling projects, can help us deal with multiple perspectives, with the challenges incurred from multiple perspectives, and with the challenges of communicating some of the insights. And I want to focus a little bit more on the stakeholder engagement. So what we saw from both case studies was that stakeholder engagement throughout the entire process helps us negotiate a shared understanding. And this shared understanding is not just beautiful so that everybody knows what everybody else sees, but it also helps us shift the policy focus away from what we originally thought was the silver bullet solution to something that is more effective and takes into account the complexity of the system. In the Guatemala case, that was the government's shift away from the effectiveness of subsidies towards diversifying farming households and introducing food emergency bags. So the stakeholder engagement helps us support reflective systems action and future thinking. Now, when we look at the actual modeling, we didn't talk about that too much, but I hope it did come across every now and then. We always try to link our results or insights back to the structure, to the feedback mechanisms that generate the results that we observe. And Daniel talked about that too. So there was behavior over time. What was it in the model that generated this particular behavior curve that was responsible for this? If we do this hard and long enough, this is a learning process where the results help us understand, where tracing the structural origins of results help us understand the system better and generate better results. But you might also have seen that this is a wonderfully cool approach to look at this structure drives behavior mantra on a fairly high level of aggregation. The Guatemala model was very rough when it came to the level of detail. We have soil organic nitrogen. Talk to an agronomist. They can go way deeper. Talk to an economist. They don't just look at price of maize on market. They go way into more detail about all these mechanisms. So this this system dynamics perspective is a fairly high-level perspective where we try to understand the interrelationships across sectors, across stakeholders, and across policy domains. But when it comes to implementing strategies or even designing business plans and performing operational analysis, I would say that's well outside the comfort zone of system dynamics. To me, where system dynamics has an important role to play is on the strategic level, on understanding the system and on generating strategic insight. Translating this strategic insight into actual operations and implementation can be better done by other approaches. So that's my sad conclusion. Is system dynamics the silver bullet solution to overcoming challenges in social ecological systems? I'm afraid it's not. But it sure is, to us at least, incredibly fascinating. And I will continue taking these supercars out to stakeholders to get a better understanding of the entire complexity of challenges that we see in these kinds of systems. And with that, I want to thank you very much for your attention. I'm going to stop sharing the screen so that I have a chance seeing people if hopefully they have questions.